All right, so we're now going to talk about the principle of dimensional homogeneity, all right, which is a really straightforward principle. It's something you inherently already know, but something you probably have never heard described as such, all right? And we're going to use that principle then to figure out the first method we can use to find dimensionless parameters, all right? So um, there's sort of the key detail here in dimensional homogeneity is, let's say, excuse me, we have an equation. Let's do the simplest equation we can think of. Right, this is traveling, right? This is the distance that an object will travel with its given initial velocity and acceleration, constant acceleration, right? So the principle of dimensional homogeneity is very straightforward. What it is that the idea that if I have an equation, everything in that equation must have the same units. Okay, so in this equation, I'm thinking about distance that has units of meters. X0 is distance, it has units of meters. V0 is velocity, it has units of meters per second. Time has units of seconds, which means this thing has units of meters. All right. 1/2 A0 t squared. All right. Meters per second squared times seconds squared gives me units of meters. So the gist here is dimensional homogeneity says no matter what the equation is, the units of all the aspects of the equation when finalized must be the same. All right, so we could think about, again, let's do our pressure equals rho GH. Pressure has units of pascals. All right, this equals kilograms per meter cubed for density, meters per second squared for gravity, and meters for our height. So this gives us kilograms per meter squared over second squared per meter cubed, right? Which is equivalent to kilograms per meter over second squared times a meter over meters cubed, right? And this is a Newton, and this is 1 over meters squared, and so this is pascals, right? Pascals on the left, pascals on the right. That's how this works. All right, that's the idea of dimensional homogeneity. So that seems like a relatively straightforward concept, but it's important if we want to develop a dimensionless parameter. All right, so the one way we can develop dimensionless parameters is if we know what the equation is. All right, so for instance, we'll go back to x equals x0 plus v0t plus 1/2 a0 t squared. All right, to develop a dimensionless parameter from this equation, we would do something like this. We're going to say we're going to create a dimensionless value of x, which is going to be x bar. And we're going to say that that is x bar times x over x0. Now, in this equation, there are two variables, right? We're saying that x is a function of t, right? So both x, we need an x bar and a t bar, right? We're going to change this into a totally non-dimensional equation. So we need x bar equals x over x0, and we're going to say that t bar equals t over t0. All right, what are x0 and t0? Well, x0 is pretty obvious, right? We can use this for x0. All right, but what is t0? These are going to be representative distances or times in our problem. Okay, so how do you come up with those? There are a lot of different ways. Let's just do the basics first, and then we'll show what happens. So from this, I could say that x equals my x0 times x bar, and t equals my t0 times t bar. And what I'm going to do is plug that into the equation up here. And so what we get is this, x0 x bar equals x0 plus v0 times t0 t bar plus 1/2 a0 times t0 t bar squared. Now, what do I do to make this dimensionless? I'm going to divide by x0. If I divide by x0, so I'm going to take this whole thing and multiply it by 1 over x0, and I get this, x bar. What are the units of x bar? They are dimensionless, right? So by the principles of dimensional homogeneity, this whole thing better be dimensionless when I'm done. So what is x0 divided by x0? 1 plus v0 t0 over x0 times t bar plus a0 t0 squared over 2x0 t bar squared. All right, now let's look at this parameter right here. We know t bar has units of nothing, right? So those are all units of nothing. V0, T0, velocity times time is some distance, right? So we have units of meters per second times seconds over meters. And if I reduce that, it has units of nothing. So this thing here, I'll circle it in red, is our first dimensionless parameter. I'll circle this guy in red too, because we can look again and say, let's see, we got units of meters per second squared times seconds squared over meters, right? This is again unitless, right? So these two parameters in front of our dimensionless variables, t bar, have become unitless and become our dimensionless parameters. So one way to get dimensionless parameters is to do something called non-dimensionalizing an equation. All right. Now we had these two parameters. We had v0, t0 over x0, and we had a0, t0 squared over 2x0. We never really said what they were. Well, x0 is really obvious. x0 is in the problem. What is t0? Well, we can define t0 in different ways. We could say that t0 is basically x0 divided by v0. So you look at units of that. We have meters times meters over seconds, and that gives us units of seconds, right? This would be one characteristic time. We could also say, if we did that, what would happen? We're going to call this pi 1. This is our first dimensionless group, and we'll call this pi 2. All right. If we use this definition, which for pi 1 and pi 2, what happens? All right. Pi 1 becomes v0 times x0 over v0 times v0, or x0, right? And this equals 1. So by using this definition of time, right, we're going to get 1 for pi 1. And over here, we'll say that we have a0 times x0 squared over v0 squared over 2x0. All right, and so this ends up equaling a0 x0 over 2v0 squared. All right, so pi 2 becomes a parameter that's important, that looks at the relative effects of acceleration to velocity in this particular problem. 100, you can absolutely do this. That's one way you could define the problem, all right? And so you'd have a pi 1 of 1 and a pi 2 of this, all right? Alternatively, you could say, well, I don't really like that definition of t0 because in this particular problem, v0 was 0. So I don't quite get, there was no initial velocity. All right, so what do I do then? Well, you could redefine t0, okay? So let's say you say, instead of that, we're going to say that t0 is x0 still over a0 squared. I'm sorry, x0 squared over this, hold on, x0 squared, blarg, hold on. I was slightly off here. We could say it's a0, right? A over x0 and the square root. That'll give you a time scale. So square root of meters per x0 over a0. Meters, and then you have meters per second squared. All right. And so this gives you the square root of seconds squared, which gives you time. All right, so now you have this square root of x0 over a0. That could be your time. If you do that, all right, then what happens? Well, you have v0 times the square root of x0 over a0 over x0. All right, you could simplify this a little bit more. So you have v0 times a0 times, 1 over the square root of x0, a0. All right, that's one possibility. And then over here, what would happen is you get a0 times x0 over a0 over 2x0, and so this becomes 1/2. All right, and so now you have this particular dimensionless parameter for pi 1, and pi 2 just becomes 1/2. Right? Absolutely acceptable, all right, for t0. All right, and then you would get this, and you might choose this time scale if you thought acceleration was more important in your problem, okay? Alternatively, you could do yet more, all right? You could say, well, I still like the idea of a time scale based on acceleration, but it turns out in my particular problem, I'm a little bit more concerned about the relative acceleration of gravity. So maybe I'll say, I'm going to say that that t0 is equal to the square root of x0 over g, where g is gravity. And if I do that, then what happens? All right, well, then I get v0 over the square root of x0g, right? And over here, I get a0 times x0 over g over 2x0, and so I get a0 over 2g, where I'm saying now I get two very distinct numbers, where I'm looking at the effects of acceleration in terms of gravity and gravity in terms of velocity. All right? So when we do this kind of non-dimensionalization, the basic thing is you're going to have a function. You're going to say that some y is a function of, let's say, x, z, t, ... Right? Whatever it is. For each one of those, you're going to say that y bar equals y over y0, x bar equals x over x0, z bar equals z over z0, t bar equals t over t0. So these are all these dimensionless versions of the variables. You then say that y equals y0, y. I'm not going to write it all down here. You do it across here. You substitute in these values into your original equation, and now your equation will end up being, and then you divide everything such that you get y bar equals a function of x bar, z bar, t bar, ... So when you divide, you're going to end up dividing everything by y0, and that gives you this equation. And then you can go back and decide what is y0, what is x0, what is z0, what is t0. You are allowed to choose what is a relevant parameter later. All right, but that's the basic scheme.